Right, good afternoon, everybody. This is Saul from Synaptec. Thank you very much for joining. I can see lots of you are now arriving in the webinar on time. Thank you for being so prompt. We'll give everyone a couple of minutes to join because I know people are back-to-back in meetings today and may take a minute to jump in. While everyone joins the meeting, please let me give you all a few housekeeping points. So we'll be recording this webinar. If you miss pieces or you're not sure what will happen, you want to review, we'll give you access to a recording of this after the event. The information that we're sharing is often available, in PDF format and on the website, which is Synaptec. So that's synapt.ec. That's our website. And of course, we've also going to have Q&A running in the background here. So we don't use the chat channel for these sessions, but you do have access to Q&A and engineers are standing by there. So if you've got questions about anything that we're discussing or any issues that we've raised, please use that Q&A because one of our engineers will try to respond to you in real time. If we don't, we'll keep a copy of the Q&A and follow up with people individually after the event. So don't worry if it looks like we're ignoring you or we didn't, answer a specific question that's only, related to your business or your needs. And then if there's time at the end, we'll try and summarize the most important ones. So today we've got some guest speakers, Dr. Stephen Blair, our head of power systems engineering, and Tom, who looks after everything to do with renewables and offshore wind in particular, which is kind of the focus for this session. So if you could move it along, Stephen, I'll just kick this off and give everyone a quick introduction here. I don't think anything we're saying on this slide is I don't think this is a surprise for anyone on this call, but cable failures have been and remain probably the single biggest item of OPEX, which is certainly unplanned in offshore wind generation. And of course, the industry is tending with projects like Dogger Bank and East Anglia 1 to go to further away out to sea, bigger cables going to 66 kV, longer sections carrying only ever more value, which just adds to the challenge and the cost of failure and repair. Now, we at Synaptec believe that more visibility and better early warning is possible to avoid failures. And one of the things that we are particularly well positioned to offer is power quality monitoring. We think it's a vital early warning system for both new projects, but also retrofitting to existing operational wind farms. Now, most people on this call are experts in the industry. You know full well that power quality itself is not a new concept and the monitoring of power quality is nothing special. However, what we're talking about here is a very complicated power system out at sea, which is remote, inaccessible, expensive and dangerous to reach. And the challenge is that power quality monitoring is often only taken place at the grid connection and not at a detailed level with the inputs into the array from every wind turbine being captured and analyzed to understand their effects on the cables that are connecting them. So the challenge here is about the number of locations and the distance that you have to cover. And our technology does this permanently and synchronously anywhere on an array. So as an introduction, we just wanted to set out here that this session is going to be about how Synaptec approaches the subject of distributed and synchronous power quality monitoring on an offshore wind farm. Stephen, if you could click for me. So very quickly about the company, because some of you may not know us, although I know Tom has been in touch with many of the people who've registered for this event. So Synaptec, you should know, is a relatively new company. We've been operational for about 6 years. And, in the simplest possible words, we invented distributed electrical sensors. That means we found out how to make the measurement of critical pressure bands like voltage and current totally passive. And these passive sensor networks are connected through the optical fiber, which is available in all power cables in offshore wind. So it's easy to access, integrate sensors at any location, retrofit them safely and easily in lots of positions, which before were maybe too difficult because they were too expensive, too complicated, required too much equipment. Things like power supplies, copper wiring, multiplexers and merging units. We eliminate all of those costs so that we fundamentally can reduce the cost and capital cost of instrumentation and improve operational costs by improving visibility, control, and in this case, predictive maintenance insights, which give you early enough warning of faults. This isn't a new concept to the industry. This technology is operational at very high voltages in transmission systems and in offshore wind today. We're also starting to explore other markets like the railways, but for today, we're going to talk about how this technology applies in this particular space. So at a very simple level, to understand the concept behind this technology that Tom and Steve are going to take you through, the thing to learn here is that we install one smart device, normally in a substation, or it could be onshore or offshore substation in this case, which connects to a single fiber, and then we can reach out over very long distances and integrate into that fiber new or retrofitted sensors. Now, these are completely passive. The only thing connecting a sensor far away from that interrogator box is encoded light traveling forwards and backwards through that cable. There is no data, and the CTs and VTs you can see here are industry standard ones. Stephen, if you want to click up the other bullets, then everyone can see, and I don't forget to say something. Thank you. So we can connect in series, like a daisy chain or a multiplexing, to use the proper terminology, up to 30, that's 30 sensors per 60 kilometers or 40 miles of standard optical fiber, which is available in these power cables. These CTs and VTs are familiar, standard devices. They're the same. We use the same equipment, and we buy from the same OEMs as the big names like Siemens or GE. But the critical point is there's only fiber connecting them. You no longer require power supplies, copper wiring, GPS clocks at these locations to timestamp. You don't require any form of digitalization using multiplexers or merging units, and you don't require a data network to bring that signal back. Everything is connected through coded light from a remote point. That's why we can go so far out and measure simultaneously and permanently so many locations at very high levels of accuracy. Also worth noting, we have already marinized this technology. So these sensors and the CTs you see here, when they're installed offshore, they're completely immune to external factors such as electromagnetic interference, varying temperatures and humidities. They've got a very wide operating range. And in fact, these devices have inbuilt and live self-calibration to adjust for ambient temperature changes. Not that there are much in the base of a TP, but it's something that we feature in the technology. And you can combine, in that budget of 30 sensors per fiber, any combination of voltage, current, temperature, strain, vibration, even humidity. And when you mix and match these sensors and these measurands, you get a lot more insights. This was designed to do protection and metering in high voltage systems, protection and control functions. But because it's so accurate and good enough for that, while there isn't a fault, it's collecting a lot of data from a lot of locations, which are giving you the early warnings and predictors of an impending failure. And in particular, looking at harmonics and power quality and power factors here. So that's the concept of the technology, and we wanted to explain that it's scalable, it reaches a lot of locations. And then very quickly, if you have a look at the next slide, and this is where I'll leave you and hand over to the experts, what we're saying here is that it is now economically affordable, and from a space and cost and footprint perspective, you can actually instrument every termination and every phase cable termination of every cable and measure discretely all the inputs into the power system that are coming from every single turbine now, to give you live and synchronous control and visibility of what's happening, not just taking an aggregate view of power quality effects and subsynchronous oscillations that might be caused at the grid connection, where arguably that aggregated view hides some of the puts and takes of factors that are out there in the array. So the concept is reaching out far, seeing lots of locations, and then at that point, we just want to slightly change the tone here, having explained that we've got the reach and the density or number of sensors that we can achieve. We now want to pass you on to the rest of the team, who are going to take you through how that's applied in real life and take a few polls along the way to see how relevant we are keeping to your expectations. So Stephen and Tom, over to you.
Thanks, Saul. Before I hand over to Stephen, and we have, I think we might have a quick poll as well before we get to Stephen. Just on this slide, I think it's useful to say, as well as measuring synchronously from all the turbines, which is useful because, as you'll hear, you don't get additions and subtractions, which you would get if you measured just at the substation end, which I think is the conventional way to do it. But you can combine those with measurements on the substation, so both at the 66 and 220 kV side, and also on the onshore substation. So you're getting this really big detailed picture of power quality. As we've mentioned, it's synchronous, so there's no need then to take it in multiple locations and try and marry up all this data. And I think if we can just go to the next slide, Stephen, is it? I'll pass on to you.
Sure, thanks, Tom. So at this point, before I start waffling on, I thought we would go for something a bit more interactive, and we will, through Zoom, activate our kind of first poll question. And this is really just to get a feel from the audience what you think are the main limitations with the way power quality monitoring is done today, mainly in the context of offshore wind. So hopefully the first poll should be activated now. If you are, would you like to activate that, Tom?
Yep, hopefully that's up for everybody, and if people just take a few seconds to vote.
So I think in this case you're allowed to vote multiple times, or there's a separate all of the above option if all of these things are challenging. Yes, so far from what we're seeing is across the board, all of these factors.
Yeah, I think it's interesting. There's not one sort of leading answer, so apart from all of the above, it appears that all those areas are of interest.
Mm-hmm. So we can maybe get a few more seconds. I think most people have voted.
Yeah, thanks very much, everyone. I'll end that, and then if we just move on to some of the applications.
Yeah, so if you end that, Tom, then we can show the results.
There we are.
Yeah, so as our running commentary was saying, kind of all of the above is the clear winner there. And it seems like for those who didn't pick all of the above, it's kind of across the board. All of these issues are affecting somebody or perceived issues. So with that in our minds, we kind of continue with some of the kind of more technical and practical aspects, and how we actually apply this in reality. So first of all, one thing I wanted to mention before getting into the kind of the main power quality aspects, one of the interesting ways that we can apply this remote monitoring solution is actually for not measuring the phase conductors, but actually measuring the current that flows through the sheath. So through the kind of return path through earth in the cables. That could be the inter-array cables or the export cable to the onshore substation. For example, this opens up quite a lot of possibilities that are quite interesting. And one example is we know it's important to monitor the continuity of the sheath to make sure it has a good solid earth connection. Typically it'll be earth at both ends of the cable, and we can monitor that over time to make sure it's still connected. It's also very useful to actually have visibility of the circulating currents in the sheath in real time. And partly that's just for determining the ampacity of the cable, so to enable better dynamic cable rating. So how much power that is flowing and how much headroom there is for more power flowing, because the currents flowing through the sheath will cause heat generation, which will impact the phase conductors as well. So it's useful to have that information. And another thing that we can do with sheath monitoring is we can look at gradual increases in the sheath currents over time. And if we look at it for long enough, we can distinguish between natural variations in the sheath current due to different wind output, but we can detect subtle increases which may indicate certain failure modes in the cable. So that's kind of the first sort of application I wanted to mention, which is kind of related to power quality. But now focusing more on what's more conventionally known as power quality. And I kind of just want to add a bit more depth to some of the points that Sol and Tom have already touched on. So with our sensing approach, for every electrical sensor, so every current and voltage sensor that we deploy, it provides permanent and synchronous monitoring of the voltage or current at that location. So what that means is we get waveform data streamed in continuously for the lifetime of that sensor. And from that waveform data, it allows us to go well beyond what you can do with like a simple RMS measurement. It means you can pick out all of the harmonics that are of interest. And that's very, very powerful. So, so for example, we would typically, for power quality monitoring, we typically deploy a 14.4 kilohertz sampling rate, which of course will give you about the 144th harmonic in principle. So that's a lot of visibility of harmonics that are available, that are present in the system. Another key factor here is that we provide granular analysis of harmonics. So we're not just looking at one location in the wind farm and trying to guess, our best guess of what's going on. We can readily deploy this at multiple locations around the wind farm at key locations. So that could be maybe at the start of the string and at the end of the string, or it could be at every individual turbine for the maximum visibility. But it means we see everything. We see every single contribution to our harmonics. So for example, one turbine might be experiencing some issue, maybe a control issue, which means it's injecting more harmonics than its neighboring turbines on the same string, and we can pick that up with this granular monitoring and immediately highlight that. Whereas some of those interactions, due to the things being in phase or anti-phase, they might actually cancel out. So you might not see that there's a problem if you're only monitoring at one location or a limited number of locations. So it means we can very quickly see when there's a deviation and pinpoint where that's actually happening. So I'll provide a kind of more concrete example of where that's actually been done before. So this is a very interesting paper that you can look at. The link is in the corner. So this is for I think one of the largest Danish wind farms out there, offshore wind farms, the Anholt wind farm. And so this is some real investigation of power quality that was done. And you can see from the plot here, which is it's basically a histogram of one of the particular harmonics. It happens to be the 17th harmonic in the voltage at one location in the wind farm. And you can see that there is a cluster of activity for that particular harmonic happening at different power levels. So this is a histogram of that activity over a certain period of time. And this was actually due to a change in the operational behavior of the operation of the wind farm, which effectively the impedances shifted over time, and it introduced a particular resonance, which meant that the 17th harmonic was promoted and amplified. So with the visibility that this power quality monitoring regime provided, it was possible to detect that resonance and actually mitigate it through control of filtering that was going on. So you can see after the intervention, after filter tuning, that 17th harmonic was brought down to acceptable levels. What's also interesting to note is that there was power quality monitoring at another location, which didn't actually see any impact from that harmonic. It wasn't an issue there because of the way the impedances worked out. There was no issue there. So it means that this granularity of monitoring at multiple locations is actually very important. Otherwise, you might miss something. So in this particular case, it meant that at the onshore connection, at the grid connection point, it reduced the impact of that harmonic in terms of grid code requirements, so that was brought down into acceptable region. And it also meant that just in general, the wind farm was operating more efficiently, so there's less losses and power dissipation due to the power from that harmonic. And it also meant that the stability was improved. So the kind of control stability of the wind farm was benefited from getting rid of that resonance. So I think that's basically exactly what Synaptec's proposal is here. Is we propose to make it much easier than has been previously possible to look at wind farms permanently, synchronously at that same level of detail that allows you to relatively easily pick out these anomalous behaviors. So for example, on the right-hand corner, we're looking at some actual data we've recorded from one of our systems, and we can see that we can detect when one harmonic, for example, does something unusual that it doesn't normally do, and we can use that information to alert the operator of perhaps this is indicative of a control issue, or it could be a component failure, or it could be a reason to adjust the maintenance schedule. And what we really want to get to, and we're on the process of doing this, is really getting to a data-driven approach to maintenance scheduling, so that maintenance can be done more intelligently and effectively, cost a lot less. And I think we've seen a lot of evidence that power quality is one of the important factors here for enabling that. So to break up the presentation a little bit here, we've going to launch another poll question. So this is really just to get your sort of immediate feedback on what we've just presented so far. Are these factors of being able to do multi-point power quality monitoring, and which is permanent, is that particularly important to you? And also, the ability to have all of the measurements synchronized from all of the different locations. So yeah, we've got quite a few answers rolling in so far.
I'll end that now then, and we'll just have a quick look at the results.
All right, that's good.
Yeah, probably thankfully for us, most people see that there is value, some or lots of value in that, which is reassuring. Yeah,
there's some skeptics in there, but the overall opinion is that this would be useful. Okay, well, I'll carry on. There's what I wanted to talk about so far next, is some of the installations that we've done so far, and what the actual data looks like, just to again show you in more realistically what it actually looks like, rather than just through slides. So one of our installations is kind of on the east coast of Scotland, where there's a test offshore turbine available. So we've instrumented that. It's been installed for about 1.5 years now, and we have data streaming from this sort of continuously, and I'll show you what that looks like in a moment. But basically, what we've done is we've instrumented the cable with current measurements at both ends, and also inside the turbine, we've deployed temperature monitoring on the cable terminations. So because we know that that's a very problematic aspect, which can cause, I think is the most significant cause of failures. Correct me if I'm wrong, Tom, but that's something that quite often goes wrong. But
yeah,
sorry, carry on.
definitely cable terminations. It's this, it's a real problem area for the industry. And then on top of that, it seems to have lacked from very much monitoring because it's so hard to do monitoring of those. So it's been interesting for us to be able to put these spot temperature measurements on cable terminations.
Yeah, because it will tell you instantly what the exact temperature at that location is. Whereas other solutions that DTS, such as DTS, they have their place where they're very useful, but it doesn't tell you the spot temperature of the termination, and that's what we achieve here. And we also have a fourth temperature measurement just to give you the ambient temperature, which could be useful as well. So that's what we've deployed here. And yeah, I think just to reiterate what Tom just said, I think it's fair to say that cables have been under-instrumented until now, and given the huge impact and cost of failures of the cable, our main proposal here is that we can add a lot of useful monitoring in a way that's very practical to install.
So this combination of doing current, whether that's on the phase or on the sheath, along with the temperature and the power quality, that can give this really holistic picture, I think.
Mm-hmm. Yep, so we'll come back to that in a moment with some data. We have another installation which is similar to the previous example, but it's doubles up on the number of strings that or export cables that we're looking at, and the distances are much more significant. So this is several kilometers out at sea, and so this will be interesting. So we get a much greater understanding of what's going on in this system. And this is actually going to be installed tomorrow, so we don't have any nice photos of this yet, but we will have, and we'll have data to be able to analyze as well, which is really the key thing that we're looking for here.
There's just one point to jump in, is to highlight how the first one you saw was for 33 kV, and this one up at Aberdeen Bay is on 66 kV, and it's just the same sensors, the same technology can do both of these cables.
Yep, and these are both retrofits as well. So it's easily attached to an existing wind farm, and of course a new install would work as well. Okay, so this is slightly out of order, but this is our first installation at the OREC facility at the east coast of Scotland. So you see on the left is our central interrogator unit, which is just installed in an IT cabinet in the onshore substation. In the center, you can see our passive CTs installed there. So I know it's a bit confusing to see what's connected to what there, but the only thing they're connected to is an optical fiber. Effectively, they don't need a power supply or a powered unit nearby to make them operate. They just connect to the fiber, and at a potentially large distance away, the interrogator unit is able to pick up those measurements. And then on the right-hand side, you can see the temperature sensors that we've attached to the cable terminations, just to monitor those. So for that first installation, this is pre-recorded, but this is the actual streaming data that we get. This is the telemetry that we get from that system. Again, this is a relatively simple installation with a low number of sensors, but here you can see a summary of all the sensor data that we get. You can see the detailed waveform information that we're collecting from there. And on the right of the waveform, you can see the harmonic spectrum for the current measurements taken there. So this has all been done continuously, and we're just taking a sort of peek at that in real time as the data is being processed. So this is something that's built into all of our electrical sensors. So you get the full waveform data, and you also get power quality data continuously. In this case, you can also see some of the temperature readings as well. And again, it's a fairly unexciting plot, as it's basically 10 degrees continuously, but we can also look at this data over a longer period of time to pick out trends and deviations from behavior as well. So So that's really the main points that we wanted to cover. So just to go over that again, this is a solution for distributed sensing, which is synchronous, so that we know the exact timestamp of every sample that we take, and we organize it so all of the sensors are sampled at the same time. So we completely eliminate that issue of needing to synchronize multiple different power quality meters. It's all taken care of, built into the platform. We've already deployed this in a number of locations, including offshore wind, and we know it works, and it's robust, particularly because it doesn't need data communications to be provisioned or other complications like GPS clocks, and it can be retrofitted to existing installations. And what we're building up with this offering is the ability to really influence the costs and hassle associated with maintenance of cables. We know that power quality, for example, can coincide with partial discharge, for example, and these sorts of indicators can lead us to more intelligent maintenance schedules and reduced outage costs, because we're finally providing a kind of more detailed visibility and monitoring of the cables, which until now, as I said, have been under-instrumented. So I think that covers it. And next, I think we're going to finish off with one last full question.
Hey, yeah, we've got a few questions, Stephen, which I hope you don't mind me sort of putting you on the spot with. We've got a few minutes left. First one is about integration to SCADA. It's been asked, is it possible to take the output from our sensors and integrate it into the existing SCADA?
Yeah, absolutely. So what we do at the moment is we provide the data in standard formats. So typically we'd use IC 61850-9-2 for sampled values. So that's to provide the waveform data in real time. But of course we can adapt to other formats as required, whatever's needed.
Great, thank you. And the next one, can we use this technology to perform fault location?
Yes, but with some caveats. So there's different approaches to fault location, and one thing that we can do that's extremely reliable is effectively perform differential protection on cable sections. So that will tell you if there's a fault in that section, but it does not give you the precise location of the fault. So that's the key thing to bear in mind. But going beyond that, there are approaches that again using the sheath measurements. If you measure the sheath current at both ends of the cable, then in principle it's possible to detect to estimate the location of an earth fault based on the ratio of the impedances. So that's possible. There's also other approaches that can be done, such as using OTDR, which we can integrate into our system, and that can give you a very precise location of faults. Again, but it needs to be a permanent fault in that case.
Yeah, it may be worth mentioning, because I think some people are from the onshore industry at this webinar, that for offshore cables, you have submarine cables where the fiber is bundled together with the three phases. So in this situation, OTDR is suitable for fault location, because if you get a phase-to-phase fault along that cable, typically it's going to be a catastrophic cable failure, which will damage the fiber as well. So you can use OTDR for fault location. And the difference is where on a lot of installations on land, you would have the fiber running separately. So I think it's probably worth highlighting that OTDR is a function we have on our platform. And should we probably got time for one last question? And this is it possible to estimate cable lifetime?
That's pretty much the critical question. So that's a very good question. I think that's obviously going to be very challenging, but what we can do, I don't think is any kind of stretch at all, is that we can very precisely and confidently monitor any kind of aberration in the voltage. So if there's for example, a transient overvoltage, we can detect that and we can log it, and we can, for example, log how many of those happen for each asset over a certain period of time. So you could say, there's 20 of those last month, for example, and we can also build up a kind of history of that asset, of what harmonics it experienced, and we can probably weight that for certain harmonics which are more likely to cause damage. So these are the things that we can build up. It's basically just an asset health history for each asset that we monitor. So I think there's a lot of power in that, and that's, as far as I know, it's never been done before at this sort of scale, with permanent monitoring, with guaranteed synchronous monitoring as well. So that's the sort of thing we're opening up, is a real understanding of the adverse conditions that these cables are subjected to. So going from that to an actual prediction of asset lifetime is quite hard, but at least we're opening the door there, because we'll have the data to start mining that and using our data science capability to try and extrapolate the answers to that sort of question.
Thanks, Stephen. I'm looking at the questions. There's a couple of really sort of quite in-depth questions, so I think that would be best if we pick up with those after by email. I think we've got one more poll to finish off with.
Sure. So our last poll here is, that should be available now. Do you think power quality data will help reduce operational costs over time? Really, we're just probing here to see if the audience sort of agrees with our proposition here, that there's a lot of untapped value in power quality data.
Just give it a couple more seconds. I see some people still voting, and then we'll give the results of the final poll. And here we are. Good to see then that people, agree, as Stephen said, there's work to be done to reduce the operational costs, but the first step is to start taking these measurements and gathering this data and beginning to learn from it. It'd be really interesting. I think we've got another slide at the end with our contact details, and if people have more questions or would like to pick up with either the engineers or myself or Saul, and we can sort of answer anything in more depth. Well, we're slightly ahead of time. I think that's probably everything we've got for today. So thank you very much to Dr. Stephen Blair and Dr. Neil Gordon, who's been busy answering all the questions in the background. So thank you very much to both of you. And lastly, thanks very much for everyone attending. It's, we've had a really good turnout today, and we will drop an email to some more people with some detailed answers in the future. So, okay, thanks very much, everyone.
Thanks. Bye.
Bye.